Students, yesterday we have studied the one of the advantages of negative feedback, and that is how negative feedback increases the input impedance and decreases the output impedance. Friends, we are aware that less output impedance is advantageous to deliver the more power without much loss, and that is being totally satisfied by means of applying the negative feedback to the amplifier. Students, now we are going to deal with types of negative feedback in this particular period. There are basically four types of negative feedback amplifiers. One is a current series feedback. Second one is voltage series feedback. Third one is current shunt feedback. And fourth one is voltage shunt feedback. Current series feedback is the type of the feedback in amplifier where output current is proportional to that of input voltage. Whatever the part of the output it is taken, or output current that flows through the load resistance, it is proportional to that of input voltage. That is in series with that of input voltage. So that's why it is called as a current series feedback. Second one is voltage series feedback. It is a type of feedback in which output voltage feedback to the input is in series with that of the input voltage or in phase with that of the input voltage. Current shunt feedback. It is a type of the feedback in amplifier, especially negative amplifier, where the output current is in shunt with that of the input voltage. Last one is voltage shunt feedback. It is a type of feedback in negative feedback in amplifier, where output voltage is in shunt with that of the input voltage. Friends, these are the different types of negative feedback amplifiers. Don't confuse, student friends. Whatever we are studying today, these are the types of negative feedback amplifier. But at the beginning of this particular topic, we studied the types of feedback. That is the difference. Otherwise, we will be gets confused. At the beginning, we studied the type of feedback. Two types. One is a negative feedback and second one is a positive feedback. And today we are going to be considering the types of negative feedback in amplifier. That is the difference. And these are of four types. Out of that, we are going to study details regarding the current series type of feedback, whose details are expected to be covered in your syllabus. As we already studied that, current series feedback is the feedback in which feedback voltage is proportional to the output current. Our output current is proportional to that of the input voltage. Our output current is in series with that of the input voltage. Such a type of the amplifier is common emitter amplifier. Is a very good example of current series type of feedback. But feedback is possible if and only if emitter bypass capacitor is not present in that. If emitter bypass is present, then whatever the feedback voltage is there, it is almost all grounded. So that's why whenever no emitter bypass capacitor is connected, then whatever the voltage across emitter resistance it is created, it is known as a feedback voltage and it is given back to the input. Such a circuitry to which we are already familiar, that is common emitter amplifier circuit, it is going to act as current series type of the feedback, and it is represented in this particular figure. Obviously, by the virtue of common emitter amplifier, we can say it consists of a transistor in common emitter configuration, where emitter is common for input as well as output. This transistor is biased by means of a power supply B.Sc and by voltage divider biasing network, which is formed by the combination of R1 and R2. This R1 and R2 provides the necessary input voltage in absence of AC supply to be amplified, so that operating point of BZT is adjusted exactly on the center of the load line in the active region, so that it is going to act as a very faithful amplifier. Along with this, the resistance Re may be combination of two resistors, or maybe it is a single resistance. It is connected to the emitter and that of ground. It is going to act as a feedback resistance. It provides the self bias to the transistor. The capacitor C is going to act as a emitter bypass capacitor, for which we are well aware. Naturally, the signal to be amplified is Vs. Rs is its internal resistance of the signal source, which is expected to be amplified. This is coupled by means of a coupling capacitor C1, Ci or Ci to the base of transistor. The amplified output is coupled to the load resistance by means of an output coupling capacitor CO. It blocks DC and allows AC to pass at the output. Thus, across the output resistance, output voltage VO is made available. But friends, this circuit has a speciality that if capacitor C is connected, then this circuit will work as without feedback. And when you disconnect the capacitor C, this amplifier is going to act as a with feedback amplifier. We are going to analyze this circuitry from the point of view of feedback concept. To analyze that, let me proceed further. Friends, to perform the analysis, as we already studied, we can say the voltage across Re without bypass capacitor C provides the feedback voltage, just now we have considered. The resistance Re carries the same current as RL carries when signal is applied. Means current flowing through the load resistance as well as current flowing through the emitter resistance are same. The AC voltage developed across Re due to output current IC is feedback at the input of the amplifier. This voltage depends on output current, and hence it is known as current series feedback. The AC equivalent circuit of the same amplifier is represented here. Look at here. Same transistor we have considered here. Vs with a signal source to be amplified. Rs is its internal resistance. Vi with the input voltage without amplified. Ii with the input current to the base of transistor. V with the voltage developed across the emitter resistance Re. IC is the collector current. RL is the load resistance. Vi dash is the voltage after feedback. Vo dash is the voltage after output voltage after feedback. So this is the AC equivalent circuit of the same. Here what we did, we have neglected the biasing network and we have grounded B.Sc directly to the ground by the definition of AC analysis, which we have studied, analysis of amplifier, in the last topic. By that particular aspect, we derived this particular circuitry from the previous circuitry. With these particular parameters, we can say the feedback factor of the network. To determine the feedback factor of the network, we have Vo dash, that is output voltage after feedback, is given as minus RL into IC. IC is the current that flows through the load resistance and RL is the load resistance. Minus sign because the direction of the collector current is opposite. V is the emitter voltage that is equal to IARE. But natural. Therefore, VE upon VO dash is equal to IARE upon minus ICRL. But we know that for current series feedback, I is equal to IC, and that's why we can say minus ICRE upon ICRL. IC will cancel, and VE upon VO dash is going to be represented as minus RE upon RL. This is nothing but the K, that is the feedback factor. The ratio of RE upon RL determines how much amount of output it is fed back to the input. This gives fraction. This gives the fraction with which the output voltage is fed back in series with the input. That is the value of K. Now we are going to determine the input resistance with feedback. That is RIF is equal to input voltage upon input current, that is VI upon II. But input voltage here, look at here, input voltage VI is equal to VI dash plus VE. Sum of both is going to be equal to VI. So that's why we can write it here that VI is equal to VI dash plus VE, which can be written as RIF is equal to VI dash plus VE upon II. By putting the value of VI in this particular equation, so as to, by splitting the term, VI upon II plus VE upon II, VI dash upon II plus VE upon II. But VI dash upon II is RI and VE is equal to IARE. Put VE is equal to IARE and VI dash upon II is equal to RI. Let me proceed further. Therefore, RIF is equal to RI plus IRE upon II. II is the input current, that is equal to base current. So that's why we can write it II, that is equal to IB equal to I minus IC. So that's why we can write this equation as RI plus IRE upon I minus IC. Take I common from the denominator so as to write I into bracket 1 minus IC upon I will cancel, and that's why we can write it RI plus I upon 1 minus IC upon I. But IC upon I, it is HFB, that is alpha. Therefore, one can write it RI is equal to RE upon 1 plus HFB, but HFB is equal to HFE upon 1 plus HFE. Alpha is equal to beta upon 1 plus beta. By using that, one can write it RI is equal to RE upon 1 minus HFE upon 1 plus HFE, which can be written as RI plus RE into 1 plus HFE upon 1 plus HFE minus A by taking LCM. This 1 plus HFE is common for this also. So that's why 1 plus HFE multiplied with 1 minus HFE upon 1 plus HFE. Naturally, the term from the denominator goes to the numerator, and we can write it RI plus RE into 1 plus HFE upon 1 plus HFE minus HFE. Next step is HFE will cancel, and we can write it RI plus RE into 1 plus HFE. But RI is equal to HIE, that is input impedance. In terms of H parameter, we can write it RIF is equal to now HIE plus RE into bracket 1 plus HFE. So this is the input resistance of amplifier in current series feedback after negative feedback has been applied. If we consider R1 and R2, now we have obtained this equation by neglecting R1 and R2. When we consider it, then we can write it RIF dash is the new feedback resistance, which is RIF parallel to R. R is combination of R1 and R2. R is equal to R1 parallel to R2. So RIF parallel to R is going to give you new resistance RIF in consideration of R1 and R2. Now we have to calculate voltage gain of the current series feedback. For that particular purpose, the H parameter equivalent model is obtained. So that is represented here. What we did here, we have replaced the transistor by using its H parameter equivalent. By neglecting biasing network, by keeping rest of the parameter as it is. Vs with the input source, HI is the input impedance which just we have represented, HFE IB with the current source to connect it to the output, RL is the load resistance, RE is the emitter resistance. By considering IB is the base current that flows through, this is the base, this is collector, whereas this one is the emitter. We have replaced the B.Sc-II by means of its H parameter equivalent. So IC is the output current, IB is the input current, I is the current that flows through the emitter terminal, that is equal to IB plus IC, RE is the emitter resistance. This is the H parameter equivalent. We are going to determine the voltage gain from this particular circuitry. To determine the voltage gain, one has to know the input voltage and output voltage, because output voltage gain is a ratio of output voltage upon the input voltage. We are going to calculate the same from this particular equivalent diagram. Our job is first to calculate the output voltage, then we have to calculate the input voltage, then we have to take the ratio of both, which is going to give you the voltage gain. Friends, by applying the Kirchhoff's voltage law to that particular circuitry, we can get VU is equal to minus ICRL and IC is equal to HFE-IB, which you already know. HFE is here beta, that remember beta is equal to IC upon IB. Therefore, we can write it IC is equal to HFE-IB. H parameters, friends, we have considered in last year. HFE is nothing but beta. Put this value in this particular equation so as to get VU is equal to minus HFE RB into RL. Let me call this as equation number 1. Now this is the output voltage which we have calculated. Now the equation input voltage VI becomes equal to HIA-IB plus IARE, and I is equal to IB plus IC. Directly I have written it. Just to split the, but IC is equal to HFE-IB, which we have considered here. Put it again in the equation so that VI is equal to HIA-IB plus IB plus HFE-IB into RE. Now take IB common from this bracket so as to get HIA-IB plus 1 plus HFE into bracket IB-RE. Now take IB common from this entire bracket so that IB into bracket HIE into bracket 1 plus HFE into RE. Let me call this as equation number 1. We have to take the ratio of output voltage VO upon input voltage VI so as to get the voltage gain after feedback. By putting those values, we can get minus HFE IB RL upon IB into bracket HIE plus 1 plus HFE RE. Naturally, IB will cancel so as to get minus HFE RL upon HIE plus 1 plus HFE RE. This indicates that as HFE is very greater than 1, we can write 1 plus HFE is equal to HFE. We are replacing this 1 plus HFE only by HFE because value of HFE beta, that is very greater than 1. Therefore, we can write it voltage gain AVF is equal to minus HFE upon RL upon HIE plus HFE RE. We have replaced this by only HFE. Thus, the voltage gain with feedback is smaller than the voltage gain without feedback. Emitter bypass capacitor means when emitter bypass capacitor is removed, then voltage gain AVF can be written as minus HFE RL upon HIE plus HFE RE. Friends, This is how we can perform the analysis of the current series feedback as one of the type of negative feedback amplifier. Dear students, here we have already completing this fourth topic, namely we can call it as it is a feedback in amplifier, where we have covered meaning of feedback, types of feedback, that is the positive feedback and negative feedback, concept of feedback, general theory of feedback, general equation of voltage gain after feedback, peculiarly equation for the voltage gain for positive feedback and negative feedback, role of positive feedback to convert amplifier into an oscillator. Then we have studied the advantages and disadvantages of negative feedback amplifier. After that, we have proved by using negative feedback how stability is increased, how bandwidth is increased, how impedance is increased, how noise is decreased, distortion is decreased, and also how output impedance is decreased. By studying the respective advantages, we concluded that it has only one disadvantage, and that is there is a reduction in gain. After that, today we have covered the types of negative feedback amplifier, where we have introduced voltage series feedback, current series feedback, voltage shunt feedback, and current shunt feedback. Out of 4, we have studied the details analysis about the current series feedback so as to calculate some of the parameters associated with the current series feedback. That's all about the topic number 4. Friends, this is the topic where we are interested to consider the numerical examples which are expected to be solved. Means definitely in the examination, numerical examples are going to be asked on this particular topic, especially to calculate the feedback factor, to calculate the input impedance, to calculate the output impedance, to calculate the bandwidth, to calculate the voltage gain, to calculate the noise, to calculate the distortion. Based on all these formulas, numerical examples are expected to be covered. Dear students, numerical examples are placed on the WhatsApp group. Try to get it solved. And if you have got any queries, any doubts, please ask me on my mail ID, on mobile number, or on WhatsApp group. So that's all about this particular topic to be considered as the feedback in amplifiers.